So folks, in your notes, in your pre-work for this, we saw a couple of formulas for calculating curvature. And the way we should think about curvature is it's a way of measuring how quickly the curve is changing at a point in time is one way to talk about it. So if a curve has a circular path to it, or kind of a partially curved path to it, how tight is that curve? And the tighter the curve, the greater the curvature. And the more smooth the curve, the more flat the curve, then we would expect the curvature to approach 0. So we saw in our pre-work for this that there were two ways of calculating curvature. And by the way, this is the Greek letter kappa. I'm not so good at drawing it. I'll try to draw it something like that. But it may just look like a K to you. But that's K for curvature, even though curvature doesn't start with a K. And we saw the first definition we were given was the derivative of the unit tangent vector when it has the arc length parameterization taken with respect to x. Okay, so again, what we're going to see as kind of a refrain for the rest of this section is that when a curve has the arc length parameterization, it's a lot easier to talk about all of the component vectors that we want to talk about. The unit normal, the principal normal, or sorry, the unit tangent normal and the principal normal, and the binormal will always be unit, so that's not really a big deal. But the first two and our expressions for both curvature and torsion are a lot easier if the curve already has the arc length parameterization. And we've seen that that's not really a big deal. We can always do that in theory as long as our curve is smooth. That means we will always be able to do the process that I showed you in the last section of rewriting the parameter from t in terms of s, the arc length parameter. Okay. So this was the first form we were shown, and the book calls this, well, the book doesn't really give this a name, I guess, other than to say that it has the arc length parameterization, but it calls the other formula the practical formula, and I think that's a really good way to think about it. This is a much more practical formula for computing curvature, but it's also messier and a little bit harder to think about as soon as you lose the fact that you have the arc length parameterization. So what we need to do is we need to look at, well, one way to say that is we're sort of scaling out the speed here to force it to have a speed of 1 is maybe one way to look at that. But we're going to take and multiply the derivative of the unit tangent vector, and we're going to multiply that by 1 over the magnitude of the velocity. Okay, that should have a vector on it. Okay, so the book called this the more practical version, and I think that's a useful way of thinking about that. Get that out of the way. Okay, so again, let me just say that this definition, the first one that I gave you, assumes that our curve has the what, folks?
Arc length parameterization?
The arc length parameterization. So just as an example, like we saw at the end, there's many ways to parameterize the unit circle, but the arc length parameterization is the one where it takes 2 pi units to travel 2 pi around that circle. Or if you went 1 second along the curve, you would have gone 1 radian along the curve. Okay? So that's that arc length parameterization. And then the second one is the alternative one. We use this, and my numbers are a little flip-flopped here. 4 should have come before 3, but it doesn't really matter. But we use the second one for any other parameterization of the curve. Okay? By the way, if you didn't know that something had the arc length parameterization, could you still use this second formula for curvature? Yes, and in fact, what would the magnitude of the velocity be in that case if it had the arc length parameterization?
1.
It would be 1, and then you would just have, sitting inside of here, you'd have a derivative sitting inside of here just like you do here. So these two are compatible, but the first one only applies if it has the arc length parameterization. Okay, so notice that the alternative definition of the curvature has a component of 1 over v of t. for this reason, curvature is only defined for smooth curves. And as a reminder, because we've said this a couple times, so what's a smooth curve again? Where r prime of t is both what and what?
Differentiable and not equal to 0.
Yes, let's be careful here because I'm already talking about the derivative, but I think that's what you meant. So the original function r is differentiable. So that means that r prime is defined. And then what, the other thing you said was non-zero. Was that Stephen there? Great.
Yes.
Thank you. Yeah, so both defined and non-zero. Thank you very much. Okay, so let's go ahead and actually compute the curvature here. And if you print this in if you open this up in Adobe PDF, you can just click the button solution there and I'll pull it up for you. But I'm going to go ahead and work through this with you. So if we want to compute curvature, I guess we have two options, folks. One, we could check to see. We could check to see if this has the arc length parameterization, and it does not. And then we could try to force it to have the arc length parameterization. But to be honest, if we did, we'd introduce some, I believe, some arc secants into the expression, and I really don't want to do that. Okay, so we're going to have to use the alternate definition, where we're going to be computing the curvature using this formula here for this problem. Okay, so notice that essentially we're going to be computing the unit tangent vector and then looking at its derivative. So let's go ahead and do so. So we're going to first compute r prime of t, which is the same thing as v of t. And that would be what in this case? Well, I'll take the derivative of the first component is 1. And then the second component, let's see, the derivative of the natural log of something is 1 over that expression times the derivative of that expression. So if you like, it's going to be 1 comma tangent of t. Now we need to, notice we got a speed component in the curvature, so we need to compute our speed, but we're also going to need, so let's go ahead and do that. So the magnitude of v of t is the magnitude of this vector here, which is the square root of 1 squared plus the tangent of t squared. But that's just the square root of 1 plus tan squared t, which is the same thing as what, folks?
Is it secant squared?
It's a secant squared t by our Pythagorean identity. Okay. Folks, normally when you take the square root of an expression that's been squared, you can simplify that, but you have to write it how? You have to write it with the absolute value of secant of t, right? But what? Well, we assume this is only for t values between minus pi over 2 and pi over 2. And on that interval, our secant function is always positive, so I can just go ahead and drop the absolute value because secant of t is positive on minus pi over 2 to pi over 2. Okay. So let's see here. We're trying to compute the curvature. We've computed the magnitude of our velocity. We've computed our speed. And we already have the unit we don't have the unit tangent vector yet, do we? So now let's go ahead and give the unit tangent vector. So t of t, the tangent vector, is r prime of t r prime of t, the vector function r prime of t divided by its magnitude. So scale down so it has every tangent vector has length 1. So that's going to be what we just found, 1 comma tangent of t over the secant of t. And we can clean that up to be, let's see here, 1 over the secant. That's the cosine of t. And if I divide tangent by secant, that's inverting and multiplying by, so we're multiplying tangent by cosine, and so we're just left with sine of t. Folks, hopefully you can see that I would make an argument that most of the problems we look at in Calc 3 are pretty cooked up so that things work out decently nicely, right? You could see that this could very quickly get exceptionally messy, and you'd be taking derivatives of messy functions, and then you'd be taking magnitudes of messy functions. It could be exceptionally messy here. Okay? So I would argue that a lot of the questions we're looking at are pretty nicely cooked up. Okay? In Calc 1, I can make up an equation on the spot and do something interesting with it. Definitely not the case with Calc 3. Okay? All right.
I have a question.
Sir.
For number 4, it says 1 over v times the magnitude of t prime of t.
Yes.
And in the question, we use just t of t. So is it t prime of t or t of t?
So we're eventually going to compute t prime of t here, because we're not there yet. Sorry about that. Yeah, so great question. We're not done with this problem. We're a couple steps yet away. So we've just computed the unit tangent vector. And so now we're going to take the derivative of the unit tangent vector. So, folks, in a way, this is not true, and I would deny it if you said I said it, but in a way, we're sort of looking at the what derivative here, folks. The second, it's like we're taking the derivative of the unit tangent vector, so it's almost like we're taking a derivative of a derivative. Yeah, I would deny that if that's what you said I said, but it's like a second derivative here. Okay? All right. So this is equal to taking the derivative of the unit tangent vector is equal to minus sine of t comma cosine of t. And so now we've got everything we need to compute curvature. So the curvature in this case is in all cases, is 1 over the speed times the magnitude of the derivative of the unit tangent vector. So that's going to be 1 over the secant of t times the square root of minus sine of t squared plus cosine of t squared. And so when everything cleans up, we get 1 over the secant of t times 1. Folks, one thing that's a little bit hard to keep track of is there's nothing that said that the derivative of the unit tangent vector had to be, again, a unit vector. Okay? But they cook up these problems so that the work doesn't get too messy. And so a lot of times you might make a misconception there. So let me just say it again. What's the magnitude of the unit tangent vector? What's the magnitude of the unit tangent vector? It's 1. Does its derivative have to have magnitude 1 at all of its locations? No. Okay, so be careful with that. In this case it does, but that was a cooked up example. Okay. So anyway, we're left with then just the cosine of t is the curvature of this. Okay. Let's remember this result because we're going to look at it on the next page. Okay. By the way, so I wanted to do an example here because a lot of the examples you look at in the text have constant curvature, or look at in the My Math Lab. And if you look at the textbook examples, a lot of them have constant curvature. So for example, a line has a constant curvature of 0. A circle, we will see, has a constant curvature of 1 over its radius. And a helix has a nice constant curvature. So a lot of the examples we look at, when you solve for k, rather than getting a function that depends on t, it's just a constant. Okay? But here I wanted to do an example where we had a non-constant curvature. The curvature changes depending on what time value we input. And we'll look at that in the example when we on the next page, actually. Okay. So folks, this was a question that was in your pre-work for this section, but I want to go through it again because it's been a little while since we looked at the pre-work. Let's give an intuitive definition of the curvature. So everyone take a minute, read through those, and take a guess at this. Lots of ways you could do this problem. The first thing I would make sure that I think it's important for everyone to notice. Oh, I'm getting some chats here. Great. That's correct, Hosanna. Yeah, very good. So the one thing I want to make sure everyone does as we work through these problems is always identify what type of object you're working with. And so notice that the unit tangent vector is a vector valued function, and we take the derivative of a vector valued function, and that's again a vector valued function, but then we take the magnitude of it, which is a scalar. Okay? Again, by the time we're done, notice in the example we had cosine of t. That's a scalar valued function. That's not a vector valued function. Okay? So certainly we can exclude these two, the vector functions, and then the intuitive definition of curvature is it's a way of talking about the rate at which a curve changes direction. Okay? Let me ask you a question. How come it isn't the rate at which it changes speed as well? Or how come it isn't, yeah, I mean, so a change in direction is going to cause acceleration, but a change in speed would also cause acceleration. So how come curvature doesn't talk about how the curve changes speed?
Because it's the unit tangent vector, and so it's not just like the velocity, it's just length 1, so it doesn't actually describe the yeah, that's what I would think.
So Dustin's exactly right. The magnitude of the velocity function would talk about speed, but we have not just the velocity function, but the unit tangent function, which always has a magnitude of 1. So that for that reason, the magnitude of t is never changing, and so when we do talk about how it's changing, all we're getting from that is information about how its direction is changing. All of the change, remember a vector can change two different ways. If you've got a vector, how could it change? It could change by changing its length, and it could change by changing its direction. But if I tell you it's a unit vector, then its length is 1 and it cannot change its length, and so the only way it will change is by changing its direction. And curvature encapsulates that. Great. Okay, folks, number 7. Everyone take a minute. Give a shot at this function here. Find its curvature. Okay, folks, I'm going to stop us because I don't want to go too far. I didn't give you a lot of room for this problem, and usually that's just because I messed up. But this time I intentionally didn't give you too much room for this problem. What's the graph of this curve, folks?
A line.
A line. Curvature measures by how much the direction of the curve, is changing. A line, by definition, is a curve that moves in a constant direction, right? That v direction that we calculated before, right? So what's the curvature of this?
0.
The curvature is 0. No work required. Okay. Now, one thing you could do is just for practice is you could compute the curvature the way we've been doing it and confirm that you get an answer of 0. And that might be a good idea. Okay, so let's talk some more about curvature. So we saw above that the curvature is the rate at which the curve changes its direction. I'm sorry, you guys probably find tons of typos in this. Another way to think about curvature is to place, this may be the first time you've seen this, folks, so let's go very slowly through this. Another way to think about this is to place a tangent circle at a point on the curve pointing in the same direction of the unit normal vector. Now, I'm gonna revisit that at the end of class after we've talked a little bit more about the unit normal vector, because you did see that in your pre-work, but you didn't really do much with it. Okay, and asking what is the radius of that circle. Okay, so what I'm saying here is maybe we've got a curve that's moving along like this, and instead of thinking about putting a tangent line at this point right here, what I'm going to draw is a tangent circle. It's a circle that's curvature matches the curvature of the curve at that point. Okay. And asking the question, what's its radius? Because as I think you've seen, and if not, I'm going to show you here in another point, the curvature of a circle is simply 1 over its radius. And so if you compute the radius of this tangent circle, then you are essentially all the way there, or you've got just one little step left to computing curvature. Okay? So let's just make sure this makes sense. The smaller the curvature, the what of the radius of the unit tangent circle. So remember, the bigger the curvature, the more this curve is bending. So if this curve has a small curvature, it's almost like a what, folks?
Larger radius?
It's going to be the larger radius. Yeah, and let's just say that one more time here. If a curve has small curvature, the smaller the curvature, the closer it's going to be to a what?
Big circle or a line.
So for the curve, the smaller the curvature, the closer it's going to be to a line. And if you were to try to fit a circle to that almost a line, you're going to have a very big radius there. Okay. Likewise, the larger the curvature, the smaller the radius of the unit tangent circle. If this curve had a really tight bend to it, at this point right here, if I wanted to put a unit tangent circle, there would be like that, something like that. Not a great drawing. But that circle would have a smaller radius because it has a larger curvature.
Why is it called the unit tangent circle?
That's a good question. I'm not sure. Let me think on that. It's also sometimes called, it doesn't have a common, people use different vocabulary for it, so it's also sometimes called the Circle of Curvature. So for the time being, let's call it that. Let me think about why. Maybe I put the word unit in there out of bad habit. Maybe it shouldn't be there. So let me think on that. But it's the Circle of Curvature is another way of thinking about it. So we went ahead and computed the curvature for this function right here on the previous page. So that was that t negative ln cosine t, and we found that it had a curvature of the cosine of t. So what is the radius of the tangent circle at any point in time?
Secant t?
Exactly. So for any point in time, the tangent circle has radius 1 over the secant, 1 over the cosine of t, which would be the secant of t. Okay. So here, folks, I ask you, what would be the maximum curvature of this curve on the interval from minus pi over 2 to pi over 2? Well, notice we could see that curvature is maximum where the secant of t is minimum. Any questions on that? So the curvature is going to be maximum wherever the tangent circle has a minimum value. And where does the secant have a minimum value on the interval from minus pi over 2 to pi over 2? At t equals 0. Okay. At that point, the curvature is what? What's the curvature at t equals 0?
1.
1. And so then what's the radius of the tangent circle?
1.
That's when it's got. That's when it's going to have the smallest radius, and that's going to be of 1. Okay. So as t approaches pi over 2, what does the radius of the unit tangent circle approach?
0.
Just careful. So let's go ahead and spell that out. As t approaches pi over 2, the and let's go ahead and approach from the correct direction. It's the only direction that works in this interval, but let's approach it from the left. As t approaches pi over 2 from the left, the curvature is going to approach the cosine of pi over 2, which is what, Dustin?
0.
Which is 0, but what does that mean that the radius is approaching? The radius of the unit tangent circle
is approaching infinity.
Is approaching infinity. Okay, so to explore that, we can click on this link. Let me go ahead and set that up real quick. So folks, let me swap this out real quick. I want to share, yes, this screen. Sorry for the delay. Okay, so here I've made a Desmos application, or I modified it, somebody else made it, so that it would show the unit tangent circle at any particular point. So here was our curve, and here I've just graphed it in 2 space. So notice that because because it was the curve t comma natural log of cosine t, that you could just use the use just the function f of x to equals the negative natural log cosine of x to describe this, because it's already because the parameterization is kind of that natural parameterization. Okay, and you can see here that I have it giving the curvature, the magnitude of it says magnitude. We don't really need that because curvature is a number. It gives the curvature as a value here, and then it's got the radius of the unit tangent circle. And what you're able to do with this is you're able to take and drag that point around. And so notice that as the point approaches pi over 2, look at the radius of that orange circle. Can you guys all see that okay on this screen that I'm sharing? Okay. So the radius at that circle, that tangent circle, and I shouldn't be calling it the unit tangent circle, to whoever asked, I don't think so. The radius of that tangent circle is quite large, but as I get closer and closer to t equals 0, the radius of that circle decreases, and it gets its smallest radius right there at 0. But then as I move further to the right, the curvature is decreasing. Right? So where does this have the tightest part of the curve? The curve is tightest right here at 0, and we can see that the tangent circle has the smallest radius at the point where the curvature is tightest, meaning the curvature is the largest value. And then the curve more and more resembles a straight line the further to the right I go, and so the corresponding tangent circle becomes larger. So there's a really nice way of thinking about the quantity of curvature. 1 over the curvature value is the radius of the tangent circle. And that's a way of interpreting that number that you get if you get a number when you calculate curvature. Okay. Folks, are there any questions on this example? I do think it's worth, so I'm giving you all these demonstrations, I do think it's worth that you guys worth spending some time on those demonstrations, because it's really important that you start to build an intuition for this stuff rather than just a rote calculation, right? If you tell me the curvature is 2.3, I think it's kind of hard to interpret that after you've just done a long calculation. But I think these sort of demonstrations allow you to get a better feel for what those things mean. Okay? And this way you don't have to worry about doing any calculations. It's all being done for you. You just get to interpret it. So let me swap back now to our notes. And then we'll just say this. Folks, the text offers a third formula for curvature. And it goes ahead and derives it, and it's an interesting derivation. It uses some of our properties of the derivatives of our vector functions, like the cross product property, the way we take the cross product rule, I believe it was called, etc. But I'll just go ahead and give you the curvature formula that you can derive, and if you're interested, see the text or see me if you want to see more information about it. But here's an alternate definition for the curvature, and sometimes, oops, looks like I'm missing well, you guys don't have it. Sometimes this may be more helpful for you to compute if you're computing curvature. Okay. And I need to swap back to this. Let me share this screen. And then I'm not going to do the derivation of the curvature of a helix. It's done, everybody does it as their example, so you can see hundreds of examples of people deriving it. And let me share this screen here. But if you're interested, I went ahead and grabbed it from the text. You can click just show me, and there's the text information for how the curvature is computed for a helix using this formula here, using the formula I just gave you. So first they compute the velocity vector function, then they compute the acceleration vector function, then they take the cross product of the two, they compute the speed and cube that, and then they look at the radius of the two here, and that's where they get the formula for the curvature of a helix. Okay? So I think it's worth looking through that. I'll let you guys copy that. There's lots of other derivations of it, and it may be worth searching for. How do you calculate the curvature of a helix? It's maybe worth looking at. But I want to just go ahead and use that information real quick. So on that page, that previous page, we saw that the curvature, oops, that didn't come out very well. The curvature for a helix is A over, what was it? Just a second here, folks.
A over a squared plus b squared?
Yes. A over a squared plus b squared. Sorry about that. I want to make a few observations on this. And the first thing, so remember, this is a helix. We were looking at a helix when we looked at the path of that eagle flying, right? And so A corresponded to what on the helix? Do you remember? A was the what?
Radius.
It was the radius, and then B was the rate of increase. And I guess I think that eagle example is really great to think of. That eagle was rising at 100 feet per minute upwards. Okay? So here we've got the curvature for a helix, and what do we notice? Okay? Well, we notice that as B approaches 0, how is the height of this helix going to be changing with time? It's going to be changing very, very slowly. And in fact, if B were 0, then even though we're thinking of this helix as being in 3 space, it would really just be tracing out a what? If B were 0, it'd really just be tracing out a what?
A circle.
A circle in the xy plane, right? It would just keep circling around itself. Okay? So as B approaches 0, the helix approaches just a circle in the xy plane. And so what's its curvature then? Well, if B approaches 0, the curvature would be approaching just a over a squared plus 0 squared, which would be approaching 1 over a. Okay? And so there's a real quick way of, if we've already assumed the curvature of a helix, of seeing that the curvature of a circle is just 1 over its radius. So let's just say that. The curvature of a circle is 1 over its radius, and all of a sudden you get to see why we were using that information when we were looking at the tangent circle at a point. It was the tangent circle's radius was 1 over the curvature is 1 over the radius. Okay. What else do I want to say? Well, I could maybe say some other things, but let's say as B approaches infinity, what does that mean for this helix? Yeah, the helix kind of begins to more and more approach a line because it's rising up so quickly that the oscillation that occurs with a cosine t and a sine t, that oscillation doesn't have as much of effect as we head upwards, right? We'd have to go quite a bit further upwards to have actually moved over. And so what we have is that the helix is going to approach a line. And what is the curvature approach? The curvature would be approaching 0 as b goes to infinity. And so that's one way of saying that is, since the curvature is approaching 0, we would say that the helix is approaching a line in shape. Okay. How are we doing here, folks? It's kind of hard to get feedback from you as I'm just doing the talking, but I think this lecture format's probably working a little bit better than having you guys do. Thank you for the thumbs up or the whatever emojis you're giving. That's great. That's really helpful. Thank you. It's hard to get feedback from you this way, but please stop me as you have questions. Please don't be saying, well, I'll figure this all out later. Ask your question when you've got a question, okay? Okay. The next thing I want to look at is the Tnb frame. Okay. So the Tnb frame is a way of creating a new coordinate system. So you want to think of this coordinate system as moving along the curve. At any point on the curve, we're going to create a coordinate system where the coordinate system is created by 3 vectors, t, n, and b, where t is the unit tangent vector. We've been looking at that. N is the unit normal vector, which we'll explore in a moment. And b is the binormal vector, which again we'll explore in a moment. Okay? So this is a really nice way of giving ourselves a coordinate system that changes with time, but everywhere makes the calculations far easier to deal with than if we just think about the original origin as being our coordinate system. Okay? So to be honest, I'm not really aware of all the applications of this Tnb frame. That's more in the realm of physics. Okay? So you may have seen this in a physics class before. If you haven't, you certainly will see it in later physics classes. Okay? But what I'd like to do is let's just do some exploring with this. And I go ahead and I give you some directions here for you to be able to pull up the exact same thing that I've got. You don't have to do this now. If you click the text file link, it just opens up a txt file that you should just save somewhere. Then you go to Calc Plot 3D, and I'll go ahead and show you how it works from here. So if you go to Calc Plot 3D, after you've downloaded that txt file that I gave you, you go to the drop-down menu, which is right here. Can everyone see my mouse okay? You go to this drop-down menu right here, you go to Scripts, and you click Load a Script, and then you're just going to go to wherever you saved those scripts that I gave you the links for. So in this case, we're taking the TNB script, and it pulls up this curve that I've made for you. Unfortunately, the guy that created this Calc Plot 3D, he did it a long time ago and hasn't updated it in years, and so this is the best way to, there's no nice way to get this information to you real quickly. Now, you can see here that I've given you a vector valued curve. Does everyone see what it is? T cosine t, t sine t, and 0.1 e to the t. This has a similar structure to what, folks? To what shaped curve?
The helix.
This is very similar to a helix in that it's still going to circle around, but with the t component in front of x and y, we're going to imagine the radius getting bigger or smaller, I guess, depending on the radius is going to change with time, eventually becoming larger and larger. And also, we're going to see that this isn't like the eagle that was rising up at a constant 100 feet per minute. Instead, this thing is going to take off exponentially into the air. Okay? So you should be able to activate this trace if you got this, and if you want to just do all this after class, that's fine. You should be able to activate this trace, and I did two things here for you, folks. the first thing to point out is that it's reading the curvature value up above. So you can see the value of the curvature is currently 0.18. That means the radius of the tangent circle is 1 over 0.18, or whatever that is. That's, something bigger than 5. A little bit bigger than 5 there. So the radius of the unit, the radius of the tangent circle, which you can see in black, and I'm sorry, I can't adjust these colors, so I'm sorry they're not very visually contrasting. But you can see the unit tangent circle there in black. Does everyone see it? So when the curvature is small, like here it's 0.1, the radius of the unit tangent circle is almost 10. And as I go along, the curvature increases. You can see that in these K values getting larger, right? As I get closer and closer, that's where the curvature is tightest. Look at that that tangent circle. That tangent circle there has a very small radius because the curvature is at its largest point there. Okay, so that's one thing to note. So unlike this is in 3 dimensions, something a little more interesting than the first example we looked at for those tangent circles and getting a sense for curvature. Okay, so as the curve gets tighter, the value calculated for the curvature gets bigger and bigger. Okay, but then the other thing to see is that I've got moving along here something called the Tnb frame. And by the way, if you're interested, you can always find this in this Calc Plot 3D by clicking the settings after you've graphed a curve, and you can ask it to put various components of the Tnb frame up for you. And that's what I had it do for us. So notice that this frame consists of 3 vectors, T, N, and B. Okay? Let me zoom in on that so we can see it a little bit better. Well, that's about the best I can do. Can you guys see that okay? I guess what I could do is let's move it along closer to the origin, then I can zoom in even closer, a lot easier. All right. By the way, you can always hit refresh to start it. If you get lost in the script, you can hit refresh and it takes you back out. Okay? And I'm going to go ahead and turn off that tangent circle because now that we've talked about it, we don't need to see it again. Unit tangent. Curvature, oscillating circle. Let's turn that off. Okay. And in fact, let's turn off the trace vector, and we'll turn off the oscillating plane for a moment. Okay. So as I'm moving this along, you can see that there are 3 vectors that are originating at whatever point on the curve I'm at, labeled T, N, and B. Okay. So T should look familiar. That's our unit tangent vector. Notice it's certainly tangent to the curve, and the length of it never changes. N is the principal unit normal vector that you learned about in the pre-work, and we're going to talk about a little bit more here. Okay? So there's our principal unit normal vector. B is the binormal vector. Now, because T has length 1 and N has length 1, what does the magnitude of B have to be?
1.
1. And the reason why you can see that is that T and N form a parallelogram, not just any parallelogram. What do they appear to form?
Square.
They form a square. The area of this square is 1 by 1, which is 1. And so B never changes. B is normal not because we had to normalize it. B has length 1 not because we had to normalize it, but will always have length 1. Because it's the cross of 2 unit normal vectors at 90 degrees. Okay? Now, so this normal vector is going to point into the direction that the curve is changing. Okay? So the unit normal vector is pointing to where the curve is going next. And as we scoot forward a little bit, we will see, yep, that curve started sort of being modified by that. You could think of as being modified by that principal unit normal vector. Okay? Now, T and N, just because I'm running out of time here, T and N together form something called the oscillating plane. Careful, not oscillating, osculating with a C in there. Okay? You can see the plane formed by these 2 vectors, right? Well, folks, how do you describe a plane? We always the best way to describe a plane, the most important characteristic of a plane is it's what?
orthogonal to a line. So you need a point and a vector.
You need a point and what type of vector, Dustin?
A normal vector.
A normal vector. And notice that our B here is the normal vector of the oscillating plane, or one of them. And we choose it with appropriate to our choice of orientation. Okay. Now, I haven't gone this far into the circle yet, or into the curve yet. I want to show you, because for a while here, it looks like this plane is sort of just sweeping along. It actually isn't. Let me zoom out a little bit. It actually isn't just sweeping along. The height is changing, right, because of that 0.1 e to the t, but it's changing very, very slowly. So this plane is not only moving in the xy plane, well, it's not in the xy plane, it's ever so slightly not in the xy plane because of this 0.1 e to the t term. Its height is slowly increasing, but very slowly, so it's kind of hard to tell that. So one way to say this is there's not a lot of twisting. There's not a lot of twisting happening of this oscillating plane. Now, as t gets larger, this 0.1 e to the t term is going to start having more of an effect, and I want you to watch what happens to the oscillating plane once the t values become positive. Look at this plane. It's starting to twist here as it rises. There's some twisting happening. Okay? Does everyone see what I mean by the plane the plane is changing? Around here, it looks like the plane is just almost just staying flat. I mean, you almost don't need 3 dimensions to talk about the plane right around here. Right around here, you don't really need that 3rd dimension. That's not really showing. You're not really seeing a whole lot. But once you get to here, this thing starts to climb up in the 3rd dimension, and it's changing out of whatever plane it's currently in. So the oscillating plane is changing. What's going to cause the oscillating, what's one way to talk about the oscillating plane changing? Well, for a plane to change, certainly the points in the plane have to change, but what else has to change?
The normal vector?
The normal vector B has to change. And roughly speaking, the way in which B is changing, the magnitude at which B is changing, is essentially the torsion of this curve. So the word torsion I want you to think of as the twisting of the oscillating plane. Okay? And that's about as good as I can do in explaining torsion. And to be honest, this is far better than I got when I was a student. They said, think of your normal vector changing, the binormal vector, the vector that's the normal of this plane, the binormal vector. Think of it changing. And so I would highly encourage you to download and manipulate this curve that I've built for you so you actually get a sense of that twisting that's happening of the oscillating plane. So around here, the torsion and the curvature are both low. Okay? Around here, both the torsion and curvature are both low. Here, the curvature is increasing, the curvature is increasing, the torsion's still staying decently low, and right here, once the t values get positive, the torsion really picks up, as does the curvature. But then the further out I go, the curvature's not going to start changing by very much, but the torsion's going to keep picking up, I think, because of that e to the t term. So folks, I encourage you to play with this because this is the concept. This is the stuff you get familiar with, and the math is supposed to inform you about this, not necessarily the other way around. I think computing torsion, I think computing curvature isn't really all that meaningful without actually looking at some curves and seeing how those curves are changing as you move along them. And so the 2 big descriptors that we have for a curve are the torsion and the curvature. And with those, by looking at this Tnb frame, frame refers to the entire coordinate system that's created by Tnb. That's those 3 vectors. That's that coordinate system that's created by them. By looking at how that changes over the curve, you really get a full description of what this curve does. Okay? I was dreading this lecture. All right. Let's look at a few more things here. Let me stop sharing on this screen, and let's see what else we can do. So although we haven't done a whole lot of computations in this section, I think that's probably the most important thing for you to spend some time getting comfortable with, is that Tnb frame and also thinking about the curvature as we move along that curve. Okay, so where did the curvature appear to be the greatest? And let's just say, I think that we saw that this was close to the origin, so this was as t was approaching 0. Okay, as t was approaching 0, the curvature appeared to be the greatest. And we could, and I unfortunately can't share both simultaneously as I'm recording this video, folks. So as t was approaching 0, that's where the curvature appeared to be greatest. So then I said, notice, and sorry, this should be in vector notation. Notice that b, the binormal vector, is just the unit normal vector of the Tn plane. And this Tn plane is also called the osculating plane. Okay. So torsion, which is denoted by tau, measures the rate at which that curve was twisting. Notice the torsion was low when my b vector wasn't changing by very much. Let me swap back one more time. When my b, so all through here, the b vector, it's changing its position, but if you look at this vector, it has the same magnitude and direction almost. So I'm talking about this red vector here. As I slide through, the red vector has basically the same magnitude, and well, it's always going to have magnitude 1, but it has basically the same direction as I move through here. And it doesn't start changing direction until about here, and now it's really starting to change direction as it goes through this. Okay? But all through the earlier values, when t was close to -10, the b vector isn't really changing its direction. It's still just basically pointing upwards in the z direction. It's ever so slightly changing, but not very much. But it's changing quite a bit right through here. And that's where the torsion starts to pick up. Switch back. Okay. So where does torsion, so I don't know if you could answer the question where does torsion appear the greatest, but the torsion appears to be the least as t is nearing a -10 for the graph, for the domain that I gave this graph. Okay, let's see, is there anything we want to add here? For the curve to twist, which vector must change? The unit binormal vector, that plane, the direction of the plane is dictated by the direction of b, the unit binormal. And folks, if I don't say unit binormal, binormal always has unit 1, so you don't need to say unit binormal on that.
Is that b right there? Should that have a vector arrow above it?
Yes. Yeah.
Okay.
Yep. So b is, this binormal is always a vector. Yeah, sorry about that. Okay. So folks, here I've got a summary of a number of the calculations we can do. To a large extent, when you do these in the homework, they're just going to be plug and chug calculations. Okay. Far more important, in my opinion, is interpreting what it is you're calculating. Okay. So I went ahead and recopied the definition of the unit tangent vector. Okay. Notice that in this case, I'm doing the unit tangent vector assuming we have what parameterization?
Arc length.
Arc length. And if it has arc length parameterization, then the speed, which is the magnitude of the derivative, is always just 1, and so we don't need to divide by the magnitude there. Okay? And notice again that a number of these equations look far nicer if you have the arc length parameterization, and as soon as you don't have the arc length parameterization, they're quite a bit messier to calculate. Okay? So the unit the book called this the principal. I haven't seen that a lot, but the principal unit normal vector, or I will sometimes just call it the unit normal vector, is simply the derivative of the unit tangent vector scaled down so that it has length 1. Okay? Now, which direction was that unit normal vector pointing in? Well, it changed. I guess it changed which direction it was pointing in. But what was something you noticed about t and n?
T is pointing the direction that the curve is going.
Okay, I agree.
And then N is pointing in the direction that the curve is turning.
That's true.
It also seems not to follow the right-hand rule.
It is if you're thinking about the Tn plane, whoever said that. It is following the right-hand rule for the Tn plane. So you're crossing T with N, not N with T, and then it is following the right-hand rule. Okay.
I got you.
So hopefully I always called it the Tn plane and never the Nt plane, because then it would be the opposite direction. But yeah, great, good observation. But more than that, folks, any two vectors always form a plane. But these two vectors are how are they related to each other? I haven't heard it yet.
They are orthogonal to each other?
They are always orthogonal to one another. Is that clear? Should the derivative should basically the derivative of the unit normal function always be perpendicular, always be orthogonal? I don't think that's always so for example, if you just took a function and then took its derivative, so if you took a vector valued function, took its derivative, and then took the dot product of the two, you would not always get 0. Why do we have that these two vectors are orthogonal here? This has to do with something that I mentioned at the start of class. It was the very first thing I mentioned in today's class, which was be in the previous video. What do we know about T of t? It's a unit vector, right?
Right.
And so what's the magnitude of it?
1.
So the magnitude is always 1. And so more generally, the magnitude is constant. And if you look back at that first proof that I gave you at the start of class today, we said that if you've got a vector valued function with constant magnitude, it is always orthogonal with its derivative. Okay? So we see here, so this is worth jotting down, we see that n, let's do it the natural direction, t dotted with n, which is of course the same thing as n dotted with t by symmetry, but that's always going to be what? 0. Because those two vectors, the unit normal and the principal unit normal, will always be orthogonal to one another. Okay. The book does derive a few of these other formulas. I don't think it's really helpful. I don't think you learn a lot by deriving these other formulas. That doesn't mean that they're not important, that they may not be helpful for you, but I'm not going to worry about deriving them. Okay. So that's the unit tangent. The unit normal then is, one way to look at it is it's simply the derivative of the unit tangent vector scaled down to force it to also have unit length. Okay. Then finally, what was b? The binormal vector. So there I do have it written correctly with the b with the arrow over the top. Well, if you so better than trying to memorize, like rather than memorizing this, folks. I mean this is true, but rather than memorizing that, I would remember that t and n together form a plane. And so if you take two vectors in a plane, their cross product is the normal vector. So the binormal vector is a vector that's the normal vector formed by these two planes. Folks, it turned into alphabet soup today, didn't it? It really turned into alphabet soup today, I feel like. And this is where all of a sudden we've got so many different ways of representing the same object that we're starting to feel a little overwhelmed. And I completely understand if that's how you're feeling. We're just going to take some time to get used to that. Okay? Here I repeated, so that you could just have one place for a whole bunch of formulas. I repeated our definition of curvature, so there's nothing new to add there. But then I gave you the definition of torsion and a couple of different ways of computing torsion. Okay. But the biggest way that I want you to think about it is it's some scaled component of the principal normal vector. We'll talk about that later if we get a chance. But more importantly, I want you to see what factor shows up in there. Did I slam? Somebody says I slammed my... Yes, it was very difficult making these notes. I've spent a week on them. Yeah. The torsion, we said, was basically a measure of how the Tn plane, the oscillating plane, was twisting. And for the oscillating plane to twist, we needed that plane's normal vector to change. Does that make sense? If there's anything I could leave you with today as far as torsion goes, it's for that oscillating plane to change, its normal vector has to change. Or for that oscillating plane to twist, its normal vector has to change. And that's where this component shows up. That's the change in the normal vector of the oscillating plane. Now, I just said change in the normal vector. We're using the word normal in a whole lot of different contexts here, and that's what's a little bit confusing. The normal vector of the oscillating plane is the binormal vector. And as that binormal vector changes, that forces your Tn plane to rotate. And that's what we mean by torsion. Okay. Where are we? We still got a little ways. All right, folks, when we pick up, actually, I'm going to assign you guys some homework, I guess. I think you guys have all the tools you need to do number 16 with the exception of 16G. Okay. So I'd like everyone to try 16A through F before class tomorrow, or before class on Thursday, so that you come in and we don't have to spend too much time on it. And the only thing we'll do is we will compute the torsion directly, although the torsion is going to come out to be 0, but we'll see how that computation works. Okay? Is there anything else I want to say? Yeah. Yes, I do need to talk about this real fast. Okay? So, folks, we will talk a little bit more next time about how I can take acceleration and break acceleration down into two component functions. Okay? So just like we would take some arbitrary, here's our, in fact we call this, well, here's x and here's y, and we took some vector like this, v, and we said v could be thought of as some a I hat plus some b j hat. We could break the vector v down into components in terms of I hat and j hat. We're going to do the same thing with acceleration in our Tn plane. So let's see here. Here's t, here's n. In our Tn plane, we're going to take the acceleration vector, which we will see next time always ends up in our Tn plane. And we're going to break the acceleration vector up into a component in the t direction and a component in the n direction. Okay? We'll call this component a sub t, just like we call this a over here. This is the a component. And we'll call this component over here, we'll call it a sub n. So that's how much we multiply we're going to treat the n and t as the same way we treat I hat and j hat in that moving frame. Okay? So it turns out that we can write the acceleration vector as I just said, you could write it as some an times the unit normal, that's times, not dot, times the principal unit normal vector, plus at times the unit tangent vector, t. So this is the same way that you would maybe break any old vector down into I hat and j hat. We're going to break our acceleration vector down into a sub n and a sub t. Okay, the normal component and the tangential component of acceleration. And I'll talk more about that next time, but I want to give you those two formulas so you can go ahead and even if we don't fully understand it, you can work through my math lab questions that go with it. And so a sub n, the component that's in the normal direction, is the curvature. So again, this is alphabet soup here, folks. It's the curvature times the magnitude of the velocity vector squared. And another way to compute that is as v cross a in magnitude over the magnitude of v. And our tangential component is just going to be the normal, well, you normally think of acceleration in Calc 1. It's going to be the second derivative of your speed vector. It's going to be the second derivative of your position vector, or another way of looking at that is that it's the, well, let's just leave it at that. It's the, you go ahead and you compute your speed, and then you take the derivative of your speed. Okay. So folks, I will talk more about these two components next time, but you do see these in your My Math Lab for this section. So I wanted to make sure that you guys could go ahead and get started on those problems. So there's nothing that says you can't get started on breaking these down into their component functions. But we'll work some examples and we'll talk more about that next time.